This demonstration examines a common precision pitch transition that combines the basic pitch transition rules illustrated in demonstrations 9 through 12. This transition shows a precise capture of an altitude from a climb, followed by an acceleration to a faster airspeed. The data plot view will be shown first, followed by the same transition shown in the flight deck view. We are initially climbing at 200 knots with a pitch attitude of 8 degrees and an EPR setting of 1.36. The plotting speed has been reduced in order to show the details of the altitude capture. At 14,942 feet, we rotate to the zero rate pitch attitude of 4 degrees in order to capture 15,000 feet while maintaining climb EPR. Notice that after the zero rate pitch attitude of 4 degrees is established, the vertical speed is still climbing. The vertical speed will reach 0 feet per minute as the altitude reaches 15,000 feet. As the airspeed increases, we must coordinate a pitch attitude reduction with airspeed to maintain altitude. This is an example of the rule that states that pitch attitude must be coordinated with airspeed changes during a constant flight path maneuver. As the airspeed approaches the target value of 250 knots, EPR must be set to 1.09 in order to maintain the airspeed constant. Using an experimentally determined altitude lead, rotate to the zero rate pitch attitude. The altitude lead depends on the rate of climb, pitch rate, and required pitch attitude change. The zero rate attitude achieves zero rate of climb at the airspeed that exists at the completion of the attitude change. After altitude capture, altitude will begin to increase with increasing airspeed if the pitch attitude is not reduced. Therefore, after reaching the desired altitude, coordinate a reduction in pitch attitude with the airspeed increase to prevent an altitude change. Slightly before reaching the desired final airspeed, reduce power to the setting that will maintain that speed. Time the power reduction so that both the desired power and airspeed are reached together. Now repeat the maneuver in the flight deck view. We're now setting the zero rate pitch attitude of 4 degrees. Vertical speed is decreasing as the altitude reaches 15,000 feet. And now as the airspeed is increasing, the pitch attitude must be reduced in order to maintain the altitude constant. Notice the coordination of pitch attitude with changes in airspeed. As we approach 250 knots, the EPR will be reduced to 1.09 in order to maintain the airspeed at 250 knots. This transition shows the precise capture of an altitude from a descent, followed by a deceleration to a slower airspeed. The data plot view will be shown first, followed by the same transition shown in the flight deck view. The initial descent is at a pitch attitude of 0 and idle thrust. The plotting speed will now be reduced to 0.1 times the normal value to illustrate the details. At a lead of 24 feet, we will rotate to the 0 rate pitch attitude of 2.6 degrees to capture 7,000 feet while maintaining the thrust at idle. As the pitch attitude is increased, the vertical speed is decreased. Even after the final pitch attitude is established, the vertical speed continues to decrease. The vertical speed will reach 0 feet per minute as the altitude reaches the target value of 7,000 feet. Now that the altitude is captured, as the airspeed decreases, an increase in pitch attitude is required, coordinating pitch with airspeed in order to maintain a constant altitude. As we approach the target speed of 210 knots, the EPR will be set to 1.05, which will maintain the airspeed constant. Using an experimentally determined altitude lead, rotate to the 0 rate pitch attitude. The altitude lead depends on the rate of climb, pitch rate, and required pitch attitude change. The 0 rate attitude achieves 0 rate of descent at the airspeed that exists at the completion of the attitude change. After altitude capture, altitude will begin to decrease with decreasing airspeed if the pitch attitude is not increased. Therefore, after reaching the desired altitude, coordinate an increase in pitch attitude with the airspeed reduction to prevent an altitude change. Slightly before reaching the desired final airspeed, increase power to the setting that will maintain that speed. Time the power increase so that both the desired power and airspeed are reached together. Notice that the final power setting was established after the final airspeed was reached. In this case, the final power setting was greater than the descent power setting. This method provided the most timely airspeed reduction. However, if the final power setting is less than the descent power setting, then the most rapid reduction in airspeed will be accomplished by setting the final power value at the beginning of the altitude capture pitch change. We will now repeat the demonstration in the flight deck view. Notice that the change in pitch to 2.6 degrees has been accomplished, and the vertical speed reaches 0 feet per minute at 7,000 feet. Now, as the airspeed decreases, an increase in pitch attitude is required in order to maintain the altitude, coordinating pitch attitude changes with airspeed changes. And as we approach a target airspeed of 210 knots, the power setting will be increased to the value necessary to maintain that speed. The altitude remains at 7,000 feet and the airspeed at 210 knots. This is demonstration number 15, part 1. Using the data plot view, it examines an alternate technique for high-performance level-offs. Although similar to the previous precision level-off, this alternate method uses an earlier altitude lead, followed by altitude capture at a reduced vertical speed. It lessens the danger of altitude overshoot when leveling off from steep climb and descent angles. We are initially climbing at 210 knots with a pitch attitude of 9.1 and an EPR of 1.36. The plotting speed is reduced to improve the details. We're now rotating to the zero rate pitch attitude of 3.4 degrees, and notice that the vertical speed is decreasing prior to reaching the target altitude of 7,000 feet. Maintaining this attitude as the airspeed increases, the vertical speed is now increasing toward the target altitude. This reduced vertical speed makes an easy capture of 7,000 feet possible. Once the altitude is captured, a decrease in pitch attitude with increasing airspeed is necessary to maintain altitude. And slightly before we reach 250 knots, we'll set the EPR to 1.06 to maintain the airspeed constant at 250. Next, we will capture 7,000 feet from a descent. We're descending at 240 knots with a pitch attitude of 0.4 degrees and idle thrust. Using an early altitude lead, we'll rotate to the zero rate pitch attitude of 2.6 degrees. Notice that the vertical speed approaches zero prior to 7,000 feet. And now maintaining 2.6 degrees pitch attitude, as the airspeed decreases, the vertical speed will now increase toward 7,000 feet. As before, this reduced vertical speed makes capturing of the target altitude easy. After altitude capture, we must increase the pitch attitude as the airspeed decreases to maintain the altitude. As we approach our target airspeed of 210 knots, we'll set the EPR to 1.05 to maintain the airspeed constant. For For steep climbs and descents, level-off errors can be large due to high vertical speeds and large required pitch changes. It is therefore difficult to judge the correct altitude lead to precisely capture the desired altitude. The high-performance level-off procedure uses an early altitude lead and the same zero-rate pitch attitude. The vertical speed then becomes zero prior to the desired altitude, after which the following airspeed change causes a gradual change in the flight path toward the desired altitude. The target altitude is then reached at a low vertical speed, making altitude interception easy and overshoots unlikely. This is demonstration number 15, part 2. Using the flight deck view, it examines an alternate technique for high-performance level-offs. Although similar to the previous precision level-off, this alternate method uses an earlier altitude lead, followed by altitude capture at a reduced vertical speed. It lessens the danger of altitude overshoot when leveling off from steep climb and descent angles. We are now approaching our target altitude at 210 knots. The plotting speed has now been reduced to show details. Using an early lead, we rotate to the zero rate pitch attitude. Which in this case is 3.4 degrees. Notice that the vertical speed approaches zero prior to reaching a target altitude of 7,000 feet. But maintaining the zero rate pitch attitude, as the airspeed increases, the vertical speed will now increase, approaching our target altitude at a much reduced vertical speed. It is therefore much easier to capture the altitude precisely. After altitude capture, we must coordinate a pitch change with airspeed change in order to maintain the altitude constant. As we approach our target airspeed of 250 knots, we'll adjust the EPR setting to a value that will maintain the airspeed constant. Next, we will be in a descent approaching 7,000 feet. Our initial speed is 240 knots. Pitch attitude is 0.4 degrees. And again, using an early altitude lead, we will rotate to the zero rate pitch attitude. This slow motion plotting speed shows the details. We're now rotating to our zero rate pitch attitude, and notice the vertical speed goes to zero prior to reaching 7,000 feet. But as the airspeed continues to slow, the vertical speed now increases toward 7,000 feet. The desired altitude is then easily captured. After capture, an increase in pitch attitude is necessary to coordinate with decreasing airspeed to maintain the altitude constant. And prior to reaching our target airspeed of 210 knots, we'll set the EPR value that will maintain it constant.